In computer science and AI, we rely heavily on formal logic to define how systems behave. At the core of predicate logic are two powerful symbols: the universal quantifier, meaning for all, and the existential quantifier, meaning there exists. Today, we will demystify these mathematical symbols using an analogy: an AI agent interacting with its environment. Understanding these quantifiers is essential for everything from defining search algorithms to formally verifying safe AI behaviors. Let's start with the universal quantifier, written as an upside-down A. It asserts that a property holds for every element in a set. Imagine an autonomous driving agent. If we state for all conditions X, the agent brakes for pedestrians, we are making a universal claim. The agent must succeed in every possible scenario: rain, snow, or shine. If it fails in even one edge case, the universal statement becomes false. It represents strict, absolute robustness. Next is the existential quantifier, written as a backwards E. This asserts that there is at least one element in the set that satisfies the property. Think of a maze-solving agent. When we say there exists a path I such that the agent reaches the goal, we do not need every path to work. The agent's task is purely to find that one specific, successful trajectory. It represents search, discovery, and feasibility. These quantifiers are deeply connected through negation. Suppose that a developer claims their agent is universally safe, meaning for all states. The agent makes no errors. To disprove this, a tester doesn't need to show the agent fails everywhere. They only need to find a single counterexample. This rule states that the negation of a universal statement is an existential statement. Formally, not for all X is mathematically equivalent to there exists an X such that not. When we combine quantifiers, the order changes everything. Consider the statement for all states X. There exists an action I that wins the game. This means our agent has a specific response tailored to every individual situation. But if we swap the order to there exists an action, such that for all stakes, it wins the game, we're describing a single magic bullet action that beats everything universally. Context dictates strategy. In adversarial AI, like playing chess, nested quantifiers perfectly describe the minimax algorithm. The existential quantifier represents our agent, searching for at least one optimal move. The universal quantifier represents the opponent, who forces our agent to consider all possible counter moves. So, the agent calculates: does there exist a move for me, such that for all possible opponent moves, there exists a counter move where I still win? These logical formulations are not just theoretical, they are the bedrock of formal verification. When we verify a neural network or a flight controller, we use automated provers to check quantifier combinations. We might ask the system to prove that for all possible sensor noise inputs within a bound, there exists a safe control output. By reducing AI behavior to these logical formulas, we guarantee mathematically sound safety boundaries. To summarize, the universal quantifier demands robustness across all states, while the existential quantifier drives the search for at least one valid solution. Whether you are debugging edge cases, designing a reinforcement learning agent, or formally proving system safety, you are constantly balancing for all with there exists. Mastering this vocabulary of logic unlocks a deeper, more rigorous understanding of how artificial intelligence truly operates.